So good morning everyone. We're a little bit late because of internet issues. So there are really few lectures left. That's why today topic lipids, and there are a few more lectures in organic chemistry. If you will need any consultation in inorganic or in the beginning of organic first classes, you can ask and we will think what we can do. Okay, so lipids today. So what are lipids? There is no general formula to describe some functional group. The Bruta formula not exist. There is no same chemical or physical characteristics can describe lipids as the one. We can say just one chemical, physical properties. Physical property is really all of them follows. They all insoluble in water, but soluble in non-polar solvents. Different solvents, but they are all insoluble in water. This is only one. It's a group of natural organic compounds, mainly derivative of fatty acids and alcohols, but not all of them. Some lipids not consist fatty acids at all. Some not consist any hydroxyl group. But mainly, this is very important to say, mainly they are derivative of fatty acids and alcohol. This definition more correct to use for saponifiable lipids. Classification I will mention soon. So, just one same property, insolubility in water. That's why they're so important to know classification of lipids, as this is only one way to divide this great number of compounds class into something with a similar structure and chemical behavior. All lipids, according to their relation to reaction, hydrolysis reaction, can be divided into two parts, saponifiable and unsaponifiable. Not just hydrolysis, but alkaline hydrolysis. Saponification, we know, it's a reaction with alkalis, sodium or potassium hydroxide. So if lipids react with the sodium or potassium hydroxide, that means undergo saponification reaction, they're known as saponifiable. If not, unsaponifiable. Each class then can be classified according to the composition. Saponifiable can be divided to parts, simple and compound, according to the complexity. Simple lipids consist only alcohols and fatty acids. During the nature of alcohol, they can be classified as waxes and fat oils or triglycerides. Only alcohols and fatty acids. Compound lipids consist something except alcohol and fatty acid, and it can be residual phosphoric acid or sphingosine alcohol. It's unsaturated amino alcohol with 18 carbons in a chain, and there can be sugars in the structure, glucose, galactose, or oligosaccharides. So these are saponifiable. Unsaponifiable themselves also can be classified. The simplest classification is classification into prostaglandins or isoprenoids. So prostaglandins and isoprenoids. More exactly, I will tell you a little bit later. So let us start with saponifiable first. To understand the structure and to write the formulae of lipids, what you exactly should do, let us start with the initial structural components. So if lipid made by alcohol and fatty acid, we need to know what alcohols and what fatty acids are there. So, structural components. For saponifiable lipids, they mainly consist few types of alcohols. It can be unsaturated or saturated fatty monohydric alcohols. Fatty means from fats. It's a long chain, long carbon chain alcohols monohydric nature. That means one OH group. Dihydric also possible to find, but seldom. And there can be trihydric alcohol, glycerol, one of the basic alcohols for saponifiable and fat oils. Saponifiable compound, complex nature. So among great number of fatty monohydric alcohols, you should this semester to know just two. It's cetyl alcohol and myricil alcohol. The structural components of very important waxes we will deal with soon. So, two types. Amino alcohols also can be in structure of some compound lipids. It's ethanolamine, common name. IUPAC name, as you know, the main functional group here, the high in priority, it's a hydroxy group. That's why it will be 2-amino ethanol, according to IUPAC, but the name is ethanolamine. It's a common and quite famous heterofunctional compound. Derivative of ethanolamine, choline, as you see, looks similar, but consists nitrogen positively charged as it bonded 4 sigma bonds to carbons. And here, among heterofunctional alcohols, can be mentioned sphingosine or sphingosine alcohol. As you see, it's amino alcohol, dihydric, unsaturated, fatty, and there are 18 carbons. It's a structural unit of all sphingolipids. And one of amino acids here, it's a serine. It's an essential structural unit of some compound lipids. So as you see, it's a heterofunctional compound, consists same moment 3 functional groups: carboxylic, amino, and hydroxy. And very important to understand one thing: in all of these cases, the carbon chain itself, there are 2 carbons. Carboxylic made this carbon chain becomes 3. But as you see, if decarboxylation of serine will happen, if it will lose carboxylic group, we will get ethanolamine. As I mentioned already, saponifiable lipids, they are mainly derivatives of fatty acids and alcohols. What alcohol there, we know now. Can be there, we know now. What about fatty acids? Fatty acids can be 2 types. They can be saturated and unsaturated, both essential to know. So among saturated fatty acids, from all great number of saturated fatty acids, you should memorize just few. Myristic acid, it's saturated with the 14 carbons in a chain. As you remember, radical, if it's saturated, it's CnH2n plus 1. So that's why it's easy to memorize. This is structural component of some plant waxes. Palmitic acid, 16 carbons in a chain, and stearic acid. These 3 enough for this semester. But you should understand different lipids, there are a huge number of them. Some can consist unique nature acids. Other lipids, for example, cannot consist ever. So in such case, structure we can understand only using some qualitative and quantitative tests, and chromatography definitely. So unsaponifiable, unsaturated fatty acids, unsaturated fatty acids, there are also few only you should memorize. This is oleic acid, one of the main structural component of olive oil. Oleic acid, it's unsaturated with 1 double bond. Take a look how we indicate that there are 1 double bond. They are same formula. We indicate total number of carbons in a chain. Here 18. Then we show how many double bonds. Here 1. And then we show where this double bond is. As here you see, it's a power. Delta power 9. That means the double bond between 9th and 10th carbon in this carbon chain. Let us check then. Linoleic acid consists 2 double bonds, but same number of carbons in a chain, 18, 2 double bonds, and they are between 9th and 10th and 12th and 13th. As you see here, they are not conjugated position. There are no conjugation. They are isolated to sigma bonds between double. It's important. Linolenic acid consists 3 double bonds between 9th and 10th, 12th, 13th, and 15th, 16th. And the last but not least, it's arachidonic acid. There are 20 carbons in a chain, 4 double bonds, and as you see, what position they are. All these acids are essential. Linoleic, linolenic, even essential such way we can sometimes accept them as a type of the vitamin. They must be present in a diet. So, about stereoisomerism. As here double bonds present in a structure for unsaturated fatty acids, that's why they are possible to find diastereoisomerism. For in our case, it's a pi diastereoisomerism, cis transposition. You should understand that we are stereospecific, so that's why our body sensitive to exact nature stereoisomers. No, like for example, amino acid in our proteins, just alpha L. Mainly only these sugars we have in our body. So for fatty acids, what should we know? Cis isomers. Being transposition usually more stable. And they are more stable. But in our body, in our lipids, structural component of cell membrane, there we're dealing with the cis isomers only. So oleic acid cis isomerism, take a look. Only cis acid known as oleic. Allydic, it's a transposition, no biochemical importance. Maybe you heard in commercial how important to have in diet proper number of omega acids. So what is omega? Classification into omega acids, it's indicate the position of the double bond according to the last carbon in the chain. If you see here 18 carbons, that means if we will calculate where the double bond is, we will see its 9th position from the backward, from the last carbon in a chain, not from the main functional group as we usually do when we go into name according to IUPAC system, but from the last, omega, the last position letter in alphabet. So this one is omega 9. As I told you, we can find this in olive oil and great number of other sources. So arachidonic acid. As you see, I draw it here quite different way. We can draw it in one line with the same as oleic acid, just now I did, but arachidonic acid is precursor of prostaglandins, and then you will see how prostaglandins look like. That's why such conformation the most acceptable. So there are 20 carbons in a chain, and this is omega-6. Take a look. From the last carbon, 1, 2, 3, 4, 5, 6 position here, the first double bond starts. That's why this is omega-6. With omega-6, usually we have no problems with. Some of them can be even synthesized in our body, like arachidonic, for example, some percentage can be. Sources of omega-6 acids, there are a huge number of them, like sunflower oil and others. So huge number. Omega-9 and omega-3, not so many. Omega-3, the main source we deal with, it's fish oil. There are a great amount of omega-3 acids. Olive oil, for example, can be source of omega-9. In diet, supposed to be all three present, but not equal concentration. So now we know main structural components. Let us talk about lipids themselves. The easiest, the simplest Saponifiable lipids are known as simple lipids, and they are vexes and triglycerides. What are vexes? Vexes are esters of higher carboxylic acids and higher molecular monohydric alcohols. What's mean? Same esters as we dealing with when we get in the product of esterification reaction. Carboxylic acid with alcohol, ester, and water. Esterification. So here same ester formula. The difference in nature of radical. Here radicals are fatty. That means big number of carbons. So that's why they are solids. Vexes are solids, and their main function of vexes protective function. So according to the can be dihydric alcohols, but not so often. Monohydric alcohols mainly. So vexes can be classified according to the nature as animal and plant. What are animal? The source is clear from animals, and here you should know the three main we're dealing with, and in medicine also. This is spermaceti, 98% of cetyl palmitate, or cetyl palmitate, more correct to say. What is 98% means? It means that not 100% of the substance. These 2% other, there are other vexes can be, other esters can be, except cetyl palmitate. Their free acid can be, there other alcohol, free alcohol also can be present. How this cetyl palmitate looks like? As I told you, it's an ester. Ester of palmitic acid with cetyl alcohol. Take a look. Palmitic acid, it's a saturated acid with 16 carbons in a chain. And alcohol here, it's a cetyl alcohol or cetylic alcohol. They are same 16 carbons in a chain, and it's saturated 1. So, the source of the spermaceti, it's a pulse. So, how to say? So beeswax, 33% of myricil palmitate, just 33. But this is the main structural component, as beeswax structural composition is unique. It consists great number of other components, other esters, and even carbohydrates. Hydrocarbons even can be found there. So great amount of difference. That's why a huge number of people suffer because of allergy. It's easy to find some allergen. So what is the structural formula? Same palmitic acid, 15 carbons in a radical, but 16 carbons total. And myricil alcohol. It's a saturated monohydric alcohol with the same number as you see carbons as hydrogen number in our radical, palmitic acid radical. So it's some life hack to memorize the formula. For cetyl palmitate, the number of carbons in cetylic alcohol same as total number of carbons in palmitic acid, and myricil palmitate, the number of carbons in alcohol radical, but it's the same as hydrogen number in palmitic acid. It's not affect the properties, it's just a life hack to memorize. And one more animal effects, very important, and we use in medicine, it's lanolin. The structural formula I will explain a little bit later. So what about lanolin you should know? It's also ester, but with a unique alcohol, cholesterol. It's alcohol monohydric also. And plant source. They are huge number. Almost all plant has own nature vex. They are protective function for our skin and for plants as well. So that's why we will not ask you to memorize the structural formula. Necessary to know that the general formula is still same. So what about fats and oils, known as triglycerides? Glycerol is an alcohol which is a basic structural component of these triglycerides. And because of its trihydric alcohol, there are 3 ester bonds to same or different fatty acids. According to the ratio between these radicals, what nature they are, saturated or unsaturated, there can be 2 types. Fats, if the greater amount, mainly it consists saturated acids. That means O2 or all 3 are saturated, in such case it's fat. Animals' nature, and they are solid room temperature. There are some exceptions. For example, fish oil, it's a liquid, but because of except such triglyceride, it consists great amount of free acids. So that's why it affects the physical characteristic, that's mean aggregate state. But mainly fats are solid. What about oils? Oils consist great amount, bigger percent of unsaturated acids. That's mean 2 or all 3 unsaturated. Plant source, liquid nature, room temperature. Standard state, room temperature we can accept. They're liquid. Exceptions also exist. Cocoa oil, palm oil, for example, they are solid room temperature. What about naming of these compounds? If we're dealing with wax, it's clear. We name it same way as the esters. But for triglycerides, somehow we need to mention these radicals and exact order. So what rules we follow to name these compounds? So first of all, because of the second carbon in a glycerol, it's asymmetrical carbon. It's a chiral center. What's mean? This second carbon has all 4 different substituents around. That's why it's asymmetrical. So the optical isomerism is possible. So that's why we can't number anyhow we want. We number carbon chain in a glycerol exact way. Starts from the top one first, and then we go second, third. This one, this numbering, we can't change. So after the carbon chain is numbered, we need to name our radicals alphabetical order, not according to their appearance, same as we do when we deal with radicals, with substituents in IUPAC naming. They should be named first with a locant, with a position of carbon it bonded to, and alphabetical order definitely. Suffix O we use instead of YLO. We can say linoleoyl, but it's hard to pronounce. That's why, according to the international system, it's acceptable that all except last, they have suffix O, except instead of IC in acid. It was linoleic, become linoleo. It was palmitic, become palmito. Something like linolenic, linoleno, oleic, oleo, and so on. So, acid name, suffix IC, we changed into suffix O. And we named alphabetical order. Last one has a secondary suffix IN, means that this is triglyceride. As you see, alphabetical order, it's the same as a numbering in our the parent chain. So that's why we can name it more simple. Linoleo, palmito, stearine. If you see that there are no numbers indicates position of these substituents, we know that this is 1, 2, and 3 according to their appearance. So we indicate numbers only if it can be different. So it's very important. Okay, so with the naming, I hope everything clear. Don't forget about alphabetical order. And if we need to classify this lipid according to the nature, is it fat or oil, we need to be sure what is the nature of radicals. Are they saturated or unsaturated? As we see here, one unsaturated, it's linoleic, one double bond there. And we have two double bonds, I'm sorry, and two saturated, one unsaturated means fat. And according to aggregate state, it will be solid, room temperature. Among all great number of chemical properties for acids, for esters, there you should know just few. No? First of all, they are saponifiable. That's why undergo alkaline hydrolysis, saponification. As example, let us take such triglyceride. According to the naming, there we have just palmitic and stearic acid in a structure. That's why palmitic according to alphabet first. That's why it will be 2-palmito diastearine. Why not indicated here 1,3-diastearine? As they are only this place, they can be 2-palmito enough to indicate. That means the rest, first and third position, they are same stearic acid radicals. So this is fat, as you can see, because of all three radicals are saturated. This compound undergo hydrolysis. I took sodium hydroxide, can be potassium, as well any alkali. Strong base, we know as alkalis. So due to hydrolysis, they are formed initial structural units. But if there will be acidic hydrolysis reaction with water with the presence of strong acid, for example sulfuric, we will get the initial components. We will get glycerol and mixture of fatty acids. But as we're dealing with the alkaline hydrolysis, in alkaline medium esters undergo hydrolysis, but they are not fatty acids are formed, but they are salts. Glycerol with the sodium hydroxide not react in such conditions, but sodium stearate and sodium palmitate are formed. 2 moles just to balance. Sodium stearate, sodium palmitate, glycerol products must be named always. Other chemical properties we usually dealing with, it's a hydrogenation reaction, stressful factor we need. That means usually in industry we're dealing with hydrogen and temperature, pressure, catalyst. As a catalyst more often we use nickel, it's a cheaper, or can be platinum or palladium even. So what we know about this reaction in industry? It's a way to produce fat from oils which are usually more cheap. That's why margarine, when we deal with, it's not so good to deal with in a diet. Why? Because of it consists hydrogenated oils. That means unnatural fats. And during their temperature, this reaction definitely needs temperature and pressure. It's a stressful factor, and it leads to cis isomers in a structure becomes trans isomers because of trans isomers more stable, and due to heating, their formation of trans acid appears. As you know, they are not good because of their substitute trans acids in our cell membrane. Problems with metabolism. So that's why hydrogenation reaction we use, but not so, let us say, not so good for our diet to use it just in great percent of them. So oxidation, it's a biochemical process. We will talk more exactly. There are different types of oxidation can be. Fortunately, no time now. And reaction with halogens. What halogens we can deal with here? No, as unsaturated fatty acids are present there, that's why as a test reaction we can use bromine water. Unfortunately, lipids insoluble in water, so that's why the emulsion is formed. But even formation of emulsion happen with the decoloration of bromine water. So we can prove that their unsaturated acids are present, not only saturated. So, but more often we deal with the reaction with iodine, non-alcohol, not water medium, but this reaction with iodine can be used for quantitative test to identify nature of lipid. Not just to say that this is fat or oil, but even be sure what kind of fat or oil is. Is it sunflower, or is it olive oil, or it's butter? So it's a way to find out, to identify the lipid even name. So there are a few characteristics of lipids. The first one, it's saponification number. It's amount of the potassium hydroxide, solid in milligrams, required saponification of 1 gram of fat or oil. So saponification number really shows number of ester bonds. That means help us to understand the percentage of triglyceride in this lipid, because of it's not 100% of one triglyceride. As you saw, they are just, we can say, mainly consist of exact nature triglyceride, but not 100% definitely. Second important characteristic, it's acid number. It's amount of potassium hydroxide in milligrams required neutralizing the free fatty acids of 1 gram of fat or oil. What this acid number shows? It shows free acids. When free acid appears due to hydrolysis, acidic hydrolysis, or storage of lipid. So that means high amount of acids mean that it's not very fresh. There are some percent of acids are present according to the quality. It should be there and they are present, but not so great. Great amount of free acid means that this lipid is not fresh. And iodine number, as I told you, it's amount of iodine in grams absorbed by 1 gram of fat or oil. So according to this iodine number, we can be sure what lipid is. For fats, iodine number much smaller than for oils. For example, olive oil consists mainly one type of fatty acid. It's oleic acid, which is one double bond only. So that's why it's not so great iodine number as sunflower, which is consists a great amount of omega-6, and there are 2-3 double bond present. So that's why, as you see, higher number. And if to compare with dairy butter, we see that doesn't matter what oil, iodine number still much higher. Because of in butter, in fats mainly present only mainly saturated fatty acids present. So what about compound lipids? Compound lipids, except fatty acid and alcohol, consist some extra structural units: phosphoric acid, sphingosine alcohol, or mono or oligosaccharides, sugars. So themselves, according to composition, they can be classified into a few types. Phospholipids can be phosphatides if they are, as alcohol, consist glycerol in their structure. Phosphatides, glycerol the main alcohol there. Sphingolipids, if they consist only sphingosine alcohol and fatty acid, they are known as ceramides. And glycolipids consist just here sphingosine also present, and consist oligosaccharides. They are known as gangliosides. But mainly our compound lipids consist few types of compounds. So for example, phospholipids can be phosphoric acid with a glycerol in a structure, and can consist phosphoric acid but sphingosine alcohol. Such lipids are known as sphingomyelins. So phospholipids, phosphatides and sphingomyelins, or phosphatides we can say also. Compound lipids, sphingolipids, can be three types: sphingomyelins if they are phospholipids same moment, and cerebrosides if they consist monosaccharides. It can be glucose or galactose. So due to the extra compound our phosphatide consists, except glycerol, phosphoric acid, and fatty acid, they can consist serine amino acid to be serine cephalins, or phosphatidyl serines or phosphatidyl serines, different way to pronounce. Phosphatidyl ethanolamines can be. Why they are amines, not amine? Because a fatty acid can be different, and that's why there are also great amount of different phosphatides possible to find. Cholamine cephalin and or cholamine, phosphatidyl cholines, lecithin. It's a other common name. What about cerebrosides? They can be two types, galacto and gluco, due to their, what is the monosaccharide there, galactose or glucose. So only one pure instant sphingolipid is ceramide. Because of only alcohol here, dihydric amino unsaturated fatty alcohol, sphingosine, and fatty acid. Let us see how all of these structures looks like, and start with phospholipids. Phosphatids first. Phosphatidyl ethanolamine as example of phospholipids. So the same structural formula for all phosphatids. The difference in the nature of amino alcohol, amino acid. Phosphatidic acid is same. So glycerol, first and second position, ester bond, bonded to fatty acid. First one is saturated, it's a nature to be, so that's why memorize. First one saturated, second one unsaturated. Then the third one bonded to the phosphoric acid and ester bond, and phosphoric acid, ester bond, bonded to the amino alcohol to be ethanolamine. Here instead of ethanolamine can be choline, can be serine. In this case it will be or phosphatidyl serine or phosphatidyl, they are just lecithin. This is the name. So saturated, unsaturated. Why it's so important? Now, first of all, in a pH alkaline 7.4, we will not find NH2 as a basic group and acidic group same moment. They will be ionized. The nitrogen positively charged, oxygen negatively charged, and they will attract to each other to form the polar head, as phospholipids are main structural components of cell membrane. So saturated, unsaturated. For unsaturated, as you remember, stereoisomerism is possible, and here cis stereoisomers only present if everything fine. So how it will looks like, I will show a little bit later. Sphingolipids, sphingomyelins, for example, they are also structural component of cell membrane. Except this. So what we know about phospholipids? Except their building blocks of biological cell membranes, they are also participate in great number of important processes, and they are very important source of acetylcholine, which is the most commonly occurred and neurotransmitter substance occurring in mammals. So you will deal with their biological function next year in biochemistry. Phospholipids, they play an important role in the transport of fat between gut and liver in digestion, and act as efficient store of energy, as well as triglycerides, fats, and oils. What about sphingolipids? They are also present in cell membrane. They are structural component, but mainly they predominate in a myelin sheath of nerve fibers. Sphingomyelin, cerebra. These names help you to understand that they are in myelin sheath. So what we know about sphingolipids also? They shows the critical role in spermatogenesis. their electrical insulation along myelinated nerves. So this was maybe not familiar for you, but you will deal with these biochemical functions soon. So what we see here, sphingosine, it's a main structural component, main initial structural unit of sphingolipids. So it's a dihydrate amino alcohol, unsaturated nature. So what we can see here, better to draw the structural formula same way as I did, and not in one line. Why? In such case, we can see there's something similar with triglycerides. And with the lipids, we just discussed phosphatids. So first, we start numbering from the main functional group. Here it's OH. So 1, 2, 3, and here if you will check, there are 18 carbons in a chain. So how sphingolipids looks like? Ceramide, the easiest one, the simplest according to the structure, sphingolipid, consists only this alcohol and fatty acid. That's why quite often sphingolipid ceramide mentioned among simple lipids, same as waxes, same as fats, oils, because of only alcohol and fatty acid. Why more often chemists insist this is sphingolipid? Why it's compound and not simple? Because of the bond different. Simple lipids, all of them are esters. I hear amide. Amide. As you see, here different nature bond. So phospholipids, as I told you, is the structural units of membrane, and doesn't matter is it sphingomyelin, is it phosphatid, polar head, non-polar tail. And except them, you can see here present cholesterol. It's also essential structural unit of our biological membrane. So, unsaponifiable lipids can be classified two types, prostaglandins and isoprenoids. So what we know about them? Sorry, something wrong here. So prostaglandins, they are derivatives of arachidonic acid. Isoprenoids can be classified two types. Terpenes, they are in plant source substances, and steroids. From great amount of terpenes, you should know just one type, carotenoids. And from great number of steroids, you will know just three types, one representative of each. You will see then. So what about prostaglandins we know? Other name of prostaglandins more often we use in chemistry, it's eicosanoids. They are signaling lipids derived from arachidonic acid metabolism that have important role in physiological and pathological processes. They are participate in very important processes. They are messengers in the central nervous system, and they are responsible, they participate in inflammation and immunity. So very active substances. So derivatives of arachidonic acid, not prostanic. Prostanic is hypothetical acid, really not found in nature. But as you see, it looks similar with what I mentioned when I gave you the structure of some fatty acids present in our lipids. They are same 20. And due to the nature of substituents bonded to the carbons in this structure, there are a huge number of different prostaglandins. Now, as example, I took one of the medicine we use, dinoprostone. As you see, there are hydroxy group, keto groups. There can be different position. Unsaturated compounds can be double bonds still present, and there can be different position. So it's a great amount of different prostaglandins possible to find. About isoprenoids, carotenoids nature. So everyone knows carotene, it's a precursor of vitamin A. Carotene also can be three types, alpha, beta, gamma. Beta, the more often we're dealing with because of its symmetrical, and of 1 mole of beta carotene produce 2 moles of retinol due to oxidation. So retinol is a vitamin A1, and about deficiency of vitamins we will talk about later. It's a next lecture. There will be vitamins mentioned, but night blindness as a deficiency of vitamin A, I think everyone knows. It's one of the symptoms of this deficiency. So, and what about steroids? Steroids, they are all derivatives of cyclopentane pyrhydrophenanthrin. Such long name, really it's a complex of few smaller parts. So what is phenanthrin? It's an aromatic compound with the same structure I did, but aromatic, 3 benzene rings. 3 benzene rings. Aromatic, that means unsaturated. If a hydrogenation reaction happens and completely, it seems like it's become saturated, full of hydrogen. Such compounds, they have prefix perhydro. So that means these 3 benzene rings, now not benzene rings anymore, are cyclohexane rings. They're known as pyrhydrophenanthrin. And 13-14 position, their cyclopentane was added, and that's why all name cyclopentane pyrhydrophenanthrin. Very important to number this compound properly. And here it's common numbering, necessary to memorize how. First of all, we number this basic part, 2 cyclopentane pyrhydrophenanthrin, 2 cyclohexane bonded to each other. So we start here from the first, in the top of the first cycle, and it's necessary to memorize that it will be number 1. And then we number the structure, the 1 structure. That means there will be 10 carbons in a chain. After this, it's simple. Next one, cyclohexane, we need to number according to the 8 and 9 present already and numbered. So we must follow clockwise. Because of 8, 9, 10 is already found in the first, but we move up with the 11th carbon in a chain. 11, 12, 13, 14. Now 5-membered ring. 13 and 14 already there. That's why we move anti-clockwise. And we have finally 17 carbons in a chain. So steroids can be classified 2 types. There can be sterols, bile acids, and steroid hormones. 1 from each. So what we know about sterols? From all great number of sterols, we need, you need to memorize just 1 structural unit. It's a cholesterol. Example. Cholesterol, it seems like something, according to commercials, that it's very bad thing to have cholesterol in our body. But cholesterol, it's a component of membrane, it's a first, and act as a cell to interconnect liquid molecules. It's a first. Cholesterol is one of the best sources of getting energy. Cholesterol, it's a precursor of such important substances of steroidal hormones, testosterone, estrogen, as well as its precursor of bile acids. Bile acids, I will show you next slide. They are so essential because of they are participate in digestion of fats and within the body of waste. So that's why, and so on. Cholesterol has also great amount of very important function, and one of them, it performs the most vital and most important function by supporting nervous system at the time of sleep. So that's why it's so important. No, not only. There are other great number of biological function. So problems caused because of when there are problems with metabolism. In such case, there these problems appears. So what we know then? Except cholesterol, we have one more. What we see about this? It's unsaturated fatty acid 27 monohydric alcohol. So cholesterol, unsaturated, they are between 5th and 6th double bond. Monohydric OH group, that's why it can form esters. And when it forms ester with some fatty acids, for example stearic or palmitic, such esters are known as lanolin. It's also wax, as consist only two types of substances, alcohols and fatty acid, with the ester bond between them. Next one, type of unsaponifiable bile acids, and only one example of them you must memorize this semester. It's a cholic acid. So cholic acid, it's trihydric. It's a, as you see, polyfunctional acid. 3 OH group, 3rd, 7th and 12th position. That's why it's so important to know how to number this ring, cyclopentane, biohydrophenane train cycles. So, and the total number of carbons shorter than for cholesterol and just 24. As I saw, they are emulsifying fats, bile acids, and cholesterol is precursor of them. And the last but not least, here steroid hormones. So estrogen and testosterone, just two you need to know. So female and male sex hormones. Cholesterol precursor, that's why deficiency of cholesterol leads to sterility. So as you see, they look similar. The difference in estrone, the 3rd position, hydroxide group, the last one, 17 here, keto group. For testosterone, quite opposite. Keto group, 3rd position, and OH group, 17th. So everything else seems similar except aromaticity for estrone first cycle. Here, not even correct to say that here alcohol group, but phenol group. For testosterone, it's unsaturated just, but double, single, double. That's why conjugated position. So in both cases, conjugation happened. What is a biological role? I hope everything clear with. So I think that's it. Yes. So here was a short information about lipids, their structure, biological role. So next year in biochemistry you will deal with their biochemical transformation and biological role. So structure and classification and structure this semester, and you should already this semester understand why then they will behave exact way, because of their structure is unique and chemistry can teach you only because of presence of some functional group is there, and chemistry will teach you. I hope you will not forget during the next semester all of this. And be careful, be ready that last checkpoint, last submodule, you should draw all of these formulae. Then every home task there will be given the list of formulae you should memorize, and you need to draw them without any sources of information open. So And doesn't matter is it online or offline, formulae you must memorize. As you see, it's a bioorganic chemistry, not biochemistry yet, but bioorganic chemistry. So I thought there will be more time, and I will use this short time I have to give you information about teaching procedure. In first division we have just 3 groups, that means 6 if we will name AB, that means 6 groups, not so many. And doesn't matter many or not, you can have some questions to ask about the Moodle. So there Mr. Dmitry, one of Vice Dean who dealing with such questions, he made a chart for those students who need consultation in Moodle. If you have any problems, I will post the link for this group. I think today's evening I will post it. You can join, you can pass this link and ask. Now, if you have no questions, if everything clear and you have no problems with, you shouldn't do this. But one thing I want to explain. The Dean's office staff, me and Mr. Dmitry, we consult you in a procedure of registration. What's happened inside the chart of the subject. So when you pass already and you were added in a Moodle of exact subject, for example, biology, anatomy, we can't affect already, and we can't help you to open some information, the lecture or practical class information. We can't help you with some checkpoints. We can't open. We have no right. I have rights to open and deal with the documents inside my subject only, in chemistry, as well as Mr. Dmitry in psychology. But biology, anatomy, we can't help inside. But if there's something you can't do and you ask your teacher and still no reply, if teacher can't help because of also don't know how to help, then you can ask for. You can ask Mr. Dmitry, you can ask us, and we will talk to the teacher. We will try to understand what is the problem, why they can't add you, or why something not opening, and so on. So this type of complaint can, but you can't ask us, as usually students do, please help me to open, help me to use information about lectures in biology subject. I can't, I have no invitation even there, I'm not a student. Okay, so for today the lecture is over. You can write and ask. No, just first group you have these topics right now. Second and third, you still have no. If you need lecture for first organic, some classification, naming, inductive mesomeric effect and so on, that's mean first organic lecture. If you can't live without, you can write in WhatsApp, and we will think about next week. I will give this information. If not, that's mean if you don't need it, that's mean next week will be RNA DNA topic, nucleic acids and vitamins. Okay, lecture is over. Please, next time, 8 o'clock morning means 8 a.m. you must be here. When I see you add yourself during 15 minutes already passed, no, it's unacceptable. It's unacceptable, and for online, offline to be late. We always start late because of necessary to connect this program, and 5 minutes usually it's lost between I start to give lecture and computer is downloaded, the program is downloaded. Not always, every week happen, but you must wait, and same moment it's open you should add, and within 5 minutes all should be present already, and not like happen again today. So If you have some questions to ask, you can ask. I don't understand what to do now. But I can't see. Okay, I don't know. What to do now? Okay, so that means the lecture is over.